Okay, good evening, students. How are you all? Now, I am going to start the revision of current electricity. Previously, we discussed some topic. Its continuation I am going to explain now. If you have any query while teaching, you write in the chat box. I will respond. Is my voice clear or not? Students, tell me. Right. The topic is that first of all, I am going to write whatever it will be. Every topic is important today. Every point is important, whatever that I am teaching. Right? Starting the class, Kirchhoff laws first. Kirchhoff laws. You know very well about the Kirchhoff laws. I am going to revise. The first one, Kirchhoff's first law. What is Kirchhoff's first law? This is also called as the junction law. Is it right? Junction rule. It is applied at the junction. Then what is this rule? Right? According to this rule, the sum of currents entering into the junction equal to the sum of currents leaving from the junction. That is the sum of currents entering into the junction. Sum of currents entering into the junction is equal to the sum of currents leaving from the junction. Sum of currents leaving from the junction. This is the junction rule. It is called as the current rule. Okay, leaving from the junction. I will explain with the diagram very carefully. You have to hear, and it was very easy. For example, this is the junction. This is the junction of the three wires. For example, this is the first wire has the resistance R1, and this is the second wire whose resistance is R2, and this is the third wire whose resistance is R3. Like this one diagram they gave, and in this, for example, the current I1 is coming like this is the I1 current, okay, and this side I2 current is flowing, okay, and these I1 and I2 are combined and traveling like this as I3. They give the diagram like this. There is one junction at here. This is the junction where the two or three wires or more than two wires are meeting with each other. At the junction, that is the sum of currents entering towards the junction. I1, I2 are entering towards the junction. There is a sum of currents entering into the junction. That is I1 plus I2. That is equal to sum of currents leaving from the junction. What are the currents leaving from the junction? That is I3. It is no need to give this type of example. Any example you can give. Right? There is a sum of currents entering into the junction equal to the sum of currents leaving from the junction. If you write like this is I1 plus I2. Okay, this one we can take as the plus of minus I3. This is equal to 0. This we can also write as the algebraic sum of currents at a junction is equal to 0. Right? This is this also junction law. The next one is the second law I am going to explain, that is called as the loop law. Okay, this is applied for the loop. Loop means it is a closed path. And according to this law, that is algebraic sum of potential differences. Algebraic sum of potential differences in a closed circuit. Algebraic sum of potential differences along a closed path. Is equal to 0. Is equal to 0. This is the second law. Is equal to 0. Okay, right. That means algebraic sum of potential differences and EMFs also. Potential differences and EMFs. Algebraic sum of potential differences and algebraic sum of EMFs in a closed circuit is equal to 0. This is the loop law. Okay, algebraic sum of potential differences and EMFs along a closed path is equal to 0. This is the second law. It was very simple. It is applied for a loop. Now let us go for the clear description of the second law. To apply the second law, there are some sign convention rules are there, okay, that you should follow, that are very important. This is according to sign convention rule. What are the sign convention rules? Okay, the sign convention rules that you should follow. Some rules to are there to apply the second law for the loop. That is the, for example, this is a resistor. then you are selecting a path that is in the direction of the current. For example, the current is flowing right side. The current is flowing right side in this. For example, you are also going right side. This is the first rule I am going to explain. This is the first rule. The first rule is that in this case you have to take the potential difference. You have to take as current always flows from high potential to low potential. This is high. Okay, this is the high potential. This is A and this is B. And here we write VB. Here VA greater than VB because the current always flows from high potential to low potential. That means VB is less. Potential difference means final minus initial you have to take. Then you have to take as minus VB minus VA. That is the you will get here VB is less minus VA more, less minus more, you will get negative. That is the if you go in the direction of the current, this is the current is going right side, you are also going right side. Okay, then you have to take the potential drop as minus IR. This you should remember. And the next second case that this is the same resistor, of the same resistor, the current is flowing in the same direction, right side, but just you are selecting, you are going in the left side. You may go left side or you may go right side. That is your wish, right? Then here this is A point, this is B point. Here A point potential is VA, B point potential is VB. You remember that always the current flows from high to low. That means VA must be greater than VB. VA must be greater than VB. Potential difference, you are going from B to A. You are going from B to A means now potential difference is you are going from where to where. This is the high potential. You know that this is high potential. This is low potential. How I know this is high and this is low? This is high, this is low because current flows from high to low. But you are going from B to A, low to high. Potential difference means final minus initial you have to take. Final is VA, initial is B to A you are going. B is initial, A is final. That's where you have to take high minus low. That is you will get as the positive. Just you remember, just like simply you can remember, if you go in the direction of the current you take negative. If you go opposite direction of the current right side, you are going left side, plus IR. If you go in the direction of the current in which direction it is going across the resistor, then if you go in the same direction, then you have to take as negative. Here this is high potential and this is low potential. When you will go high to low, potential drop occurs. Potential drop you have to take negative. But here when you go from low to high, potential rise occurs. Potential rise you have to take as positive. Okay, right. And the next one is this is across the resistor. Okay, this is A and this is B, right? And this is A point and this is the B point. And C I will explain. If in D I will explain. That is across the cell. Okay, if any cell comes it here, this is a cell, this is a cell. Okay, now this is a positive terminal and this is a negative terminal. Its EMF is E. For example, you are going from positive to negative. Okay, you are going from positive to negative, whatever it may be the direction of the current across the resistor. We can consider the direction of the current, whether you are going in the direction of the current or opposite direction of the current. But across the cell, you don't bother about the direction of the current. Just you have to take. When you will go from positive to negative, then you have to take as potential drop as minus. You are going from positive to negative. Now the last diagram is that this is the same cell. Okay, this is the positive terminal and this is a negative terminal. This is A point and this is B point, and you are going from negative to positive. You are going from negative to positive. That means you have to take as the potential difference as positive plus EMF plus E. Okay, these are the sign convention rules. Just while passing across the cell, you don't consider the direction of the current, whatever it may be the direction of the current. Just you think about the positive to negative. If you go from negative to positive, you have to take positive. If you will go from positive to negative, you have to take negative. You see here, I'm going from A to B. That means this arrow mark is that direction along that I am going. That is, I am going from positive to negative. You should take negative. If you here, I'm taking the below this arrow mark I drawn. That is direction of the motion of person, and I am selecting a loop. That is, I am going from B to A, negative to positive. That means positive you have to take. Negative to positive means this is negative side is the low potential. This positive side is the high potential. Now low to high I am going means difference क्या हो जाएगा? difference is nothing but final minus initial. High minus low is positive. You here we are going that positive to negative we are going. That means high to low I am going. When you go from high to low, right? When you go from high to low, this is how I know that a high and low. This positive is the high potential, negative is the low potential. High to low you are going means potential difference. Potential difference. Final minus initial. Okay, this is initial, this is final, right? Low minus high gives negative like this. Okay, it was very simple. Okay, you can remember in any way. Just it was very simple to remember that if across the resistor, if you go in the direction of the current, negative. If you go upward direction of the current, positive. If you go from positive to negative terminal of the cell, negative. Negative to positive of the cell, then positive. These are the sign convention rules. Have you understood, students? These sign convention rules are very important. If you not understood this one, then you cannot able to understand the next one. Okay. One application we will discuss based on this. Okay, students, I'm going to erase this. If you have any query, you can write in the chat box. Do it fast, students. What we are doing it here in the sign convention? Potential drop you have to take as potential drop you have to take as negative. Potential rise you have to take as potential rise you have to take as positive. Increase in potential is positive, decrease in potential is negative. Can I erase? Do you have any doubt, students? Do it fast. Tell me. If you have any query, write in the chat box. Okay. Can I erase? Can I go for the next topic? Okay, students. Now, one application I will explain based on this. Then later I will start the Wheatstone bridge. An example in which we are applying the flash. Find the current. Find the current in following circuit. Okay, in the following circuit we have to find out the current that is based on the Kirchhoff laws. Then for the purpose, this is considered as a cell whose EMF is E. Okay, and this is a first resistor. This is a positive terminal and this is a negative terminal. Okay, and this is the first resistor whose resistance is R1, and this is the second resistor. This is the first cell E1. Okay. Mm. There are two cells are there here. Okay, we are connecting like this. This is the first resistor, this is the second resistor, this is the third resistor. There are three resistors they give. Then the question is that they are asking to find the direct current value in this. Find the current in this. Current starts from the positive terminal of this battery. Okay, current starts from the positive terminal of this battery, and it will go like this, like this, like this, like this, like this. Then in this I current flows. Then what is the value of I that we have to find out? Then for the purpose you have to select a path. This is A, B, C, D. I am taking. Now you select a loop. Apply the second law. Okay, loop law. Then according to the loop law, okay, what is loop? You have to select a loop. It is A, B, C, D, A. Anything you can select. That means you are going from A to B, B to C, C to D, D to A. Like this I am going. Right? You may go from A to D, D to C, C to B, B to A. You can select some path. Okay. You can select some path. Here I am selecting the ABCDA loop. Okay. Apply Kirchhoff's second law, right? According to Kirchhoff's second law. What we write Kirchhoff's second law? According to the Kirchhoff's second law, we can write like this. That is algebraic sum of potential differences and EMFs in a closed circuit is equal to 0. We have to start from A to B. We gave that A B C D A loop. A to B we have to go. We are going in the direction of the current, right? We are going in the direction of the current across the resistance. You have to take negative, right? According to the rule, minus IR1. Then next A to B completed. B to C I am going. In direction of the current I am going. Potential drop minus IR2. Next C to D I am going. C to D. A to B, B to C, C to D. C to D is also in the direction of the current I am going. C to D I am going. Current also C to D. That means I am going in the direction of the current. Anyhow, take negative. Then next I am going from D to A. D to A I am going. First one cell occurred. This cell, you don't bother about the direction of the current at here. You have to check whether you are going from negative to positive of the cell or positive to negative of the cell. Then D to A I am going. D to A I am going. At D side negative is there, A side positive is there. That means negative to positive I am going. When you go from negative to positive, then you have to take positive. Then next, here one more cell occurs. That is a negative to positive you are going. Again you have to take plus. That is a plus E1. Then you simplify this. Then you will get this one like this. That is I of R1 plus R2 plus R3 is equal E1 plus E2. Then we will get as I is equal to E1 plus E2 by R1 plus R2 plus R3. Like this we have to find out the current in a circuit, complex circuit based on the Kirchhoff's second law. Right? Students, is it clear? Next topic is very important. I'm going to explain. Right? Next topic is the, you know that Wheatstone bridge. Wheatstone bridge. What is Wheatstone bridge? Wheatstone bridge is the arrangement of four resistors. Okay. What is the Wheatstone bridge principle? Now you see here very carefully. This is the one resistor whose resistance is P, and this is another resistor whose resistance is Q, and this is one more resistor whose resistance is R. Okay, and this is one more resistor, that is S. There are four resistors are there now. These four resistors are arranged like bridge. These are, this is A, B, C, D we will take. Okay, and at A, between A and C, we will connect to one battery whose EMF is E, and this is a plug key, right? Now, let us go for, and we will connect one galvanometer between B and D. This is a galvanometer. Now, we have to go for the current distribution. For example, I current starts from the positive terminal of the battery. After coming to this point, the current will goes splitting, and this side the I1 current flows, and this side I2 current flows. This side I1 current, and this side I2 current. Now, after coming to this point, again the current will be splits. Okay, the I1 current is going this side, I1 current is going this side. That I1 will be split into two parts. This is the current for the galvanometer is we can take as IG, and this side is I3 we will take. I3 current is coming this side, IG current is coming this side, right? And I2 current is coming this side. This I2 and IG will be combined, and this side it will go as I4. First you do the current distribution. First you do the current distribution. I3 and I4 again combine, and in outside the current is I. This is the current distribution. What happening here? It was very simple. I current is coming to this point. It will split into two parts. I1, I2. Then after I1 come to point B, again splits. I2 is already completed. I3, IG. This side IG is coming. This side I2 is coming. These two combinedly goes this side. That is I4. This I3 is coming. I4 is coming. This will combine and travel as I. This is the current distribution. Okay. Now, what is Wheatstone bridge principle? What is the Wheatstone bridge principle? The principle is that very simple. That is, when current through the galvanometer is zero, when current through the galvanometer is zero, IG means current through the galvanometer is zero. Bridge is said to be balanced. Bridge is balanced. Then P by Q equal to R by S we will write. P by Q is equal to R by S. When current through the galvanometer is zero, then P by Q equal to R by S. This is the Wheatstone bridge principle, right? Then what is PQRS? PQRS are the resistances resistances of four resistors which are connected to form a bridge. Resistances of four resistors, four resistors, right? And now let us start its proof. We have to go for the proof of this one. And for the purpose, what we have to do it here, it was very simple to prove it. First apply the junction rule. Apply junction rule. Okay, apply Kirchhoff first rule, Kirchhoff current rule, that one. Kirchhoff first law, Kirchhoff's first law means junction law. Okay, apply Kirchhoff first law. At what point we have to apply? At junction B apply. At junction B, yes, what is the Kirchhoff first law at junction B? Junction B entering current is I1. I1 leaving current is what? Ig is leaving, I3 is leaving. Then we write as I3 plus Ig. Sum of entering current equal to sum of leaving current. I1 is entering to B and I3, Ig are leaving from B. That's why entering sum is I1. Leaving sum is I3 plus Ig. From B, what are the leaving currents? I3 and Ig. What are entering currents? I1. I1 equal to I3 plus Ig. We write this is equation 1. Okay, right. And next, or you can keep it like this, and then at the junction D also you can apply. At junction D, what we have to apply? What are the entering currents to the junction D? Ig is coming this side and I2 is coming this side to the D. That means sum of entering currents are I2 plus Ig. That is, what are the leaving currents? This side from the D only one current is leaving, that is I4, right? Completed. Junction rule is completed. Next, this is equation 1 and 2. And the next, apply the Kirchhoff second law. Apply Kirchhoff second law. Then Kirchhoff second law we have to apply. For what we have to apply for the Kirchhoff second law? Kirchhoff second law we have to apply for the loop, right? It is a loop law. That's why you have to select the loop. First I am selecting a loop A, B, this side triangle, left side triangle. Okay, and next you select the right side triangle. That means the loop left side triangle is A, B, D, A, A, B, D, A. Right side triangle is B, C, D, B, B, C, D, B. Right, two loops you have to select. Now, first loop A, B, D, A. I am selecting. Your wish. You may select A, D, B, A also. Okay, but you have to select the two loops. Okay, and then the first one A to B I am going. A to B in the direction of the current I am going across the resistor. Potential drop occurs. Potential drop you have to take in the direction of the current you are going means negative you have to take minus IR. Current is I1. Resistance is P minus I1 P. Next, B to D I am going. A to B completed. B to D I am going. B to D means you follow the cursor. B to D I am going means in the direction of the current I am going. Then the Ig current into resistance you have to write minus IR again. Ig into resistance of the galvanometer I will take as G. Next, D2A, 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 D2A means current is going from A to D. I am going from D to D, D to A. Upward direction of the current I am going. That's why you have to take as I to R. The sum of initially came A point. We started at A point and then we ends at A point. Then closed loop is completed. Algebraic sum of potential drop should be equal to 0. Right? Now you substitute. This is equation 3. Have you understood? If you have any query, write in the chat box. Okay. Next, another loop we will take. Right side B C D B, B C D B, B C D B, B to C. In the direction of the current I am going. Minus IR. I is I3. B to C, B to C. In the direction of the current I am going. Minus IR. Potential drop should be negative. Minus I is I3. R is Q. Minus I3Q. Minus I3Q. Next, C to D I am going. B to C completed. C to D. C to D. Next to D to B. C to D up means I am going C to D, but the current is going D to C. Upward direction of the current I am going. You have to take SIR. I is I4. R is S. Next, D to B. Upward direction of the current I am going. Right, current is going from B to D. I am going from D to B. D to B. B to C completed, C to D completed, D to B, then that is plus IgG is equal to 0, equation 4. Have you understood this? Right, understood now? Okay, now what we have to do, we have to do little thing, that is adjust the values of P, Q, R and S. Okay, adjust the values of P, Q, R, S and make galvanometer deflection as 0. Galvanometer deflection as 0. Galvanometer deflection as 0. Then you write Ig 0. Then what you have to do, you have to adjust the P, Q, R, S. By adjusting that, you have to make the galvanometer deflection as 0. When the galvanometer deflection becomes 0, this condition substituted in this condition substitute in above above equations. If you substitute in above equations, then what you will get? What you will get, right? Very important. Every point is very important. But then what you will get from equation 1, 2, 3? From equation 1, 2, 3 and 4, what you will get? Just Ig0 you write here. I1 is equal to I3, we will get I1 is equal to I3. This is equation 5. Next, here Ig0 you write. I2 is equal to I4, you will get. This is equation 6. Next, here you write Ig0, this term will become 0. Then minus I1p plus I2 are equal to 0. Minus I1p we will take to right side. Then we will get I1p is equal to I2r. This is equation 7. Next, equation 4. Equation 4, Ig0 you write, this term you write 0. This term will become 0. Minus I3q take right side. Minus I3q take right side. If you take minus I3q right side, this is 0. Minus I3q plus I4s equal to 0. Minus I3q taken right side, I3q equal to I4s. I3q is equal to I4s. This is equation 8. Now divide both of them. Equation 7 by equation 8 you can do. Okay, right? Then what you will get? I1p by I3q is equal to I2r by I4s. But here one thing is, remember that. What is that one thing you have to remember? It was very simple to remember that here P I1 is equal to I3 from equation 5, from equation 6, I2 equal to I4. They will be cancelled with each other, right? I2 I4 cancel because of equation 6, I1 I3 cancel because of equation 5. Then what remains? The final formula remains is that P by Q equal to R by S. That means we substituted the current through the galvanometer as 0. Then we got as P by Q equal to R by S. This is the principle that we proved. Is the Wheatstone bridge principle. What is that Wheatstone bridge principle? That is when current through the galvanometer is 0 in this bridge. Okay. The arrangement of 4 resistors in the shape of bridge, that is called as a Wheatstone bridge. Wheatstone is the name of the scientist, right? When the current through the galvanometer is 0, at that moment the ratio of this side resistances P by Q equal to R by S. Okay, understood students? Clear? Clear? Is it clear? Tell me fast. Right, let us go for the next one. I'm going to erase this. If P by Q equal to R by S, current through the galvanometer is 0 means this galvanometer part we can remove. Galvanometer part we can remove. When we remove the galvanometer part, then you will get like this. You can find the effect resistance in this. Okay, that you will learn in clearly in you follow the previous placed lectures. Okay. Next, I am going to revise the meter bridge. Right. Next topic is the meter bridge. What is meter bridge? Meter bridge is the practical form of Wheatstone bridge. Practical form, that is the which it is based on, it works based on Wheatstone bridge principle. Based on Wheatstone bridge principle. Do you know what is the Wheatstone bridge principle? When current through the galvanometer is 0, then P by Q equal to R by S. Okay, meter bridge, it is a practical form of Wheatstone bridge. You learn the practical, right? Practical form of meter bridge, practical also we discussed. Practical form of Wheatstone bridge. Wheatstone bridge is a concept. Practical form is meter bridge. Let us go for the construction and working of the meter bridge. Let us see here. This is a meter bridge has two L-shaped copper strips. This is the first one. This is the second one. You see here, this is A point, this is B point. These two are L-shaped copper strips. Here there is a 1 meter length manganese wire is there. This is the 1 meter length manganese wire. Beside of this, there is a some scale is there. Okay, some scale. Okay, in the middle there is a rectangular copper strip they will place. Okay, and there are two gaps are there. This is the left gap and this is the right gap. In the left gap they will place the, in the left gap they will place the unknown resistance, the wire whose resistance we want to determine, that we will place. This is X that we have to find out. In the right gap we will place the resistance box whose resistance we know, right? And next, this is 1 meter length manganese wire. This is the manganese wire. Its length is 100 centimeters. Length is the 100 centimeters because it is 1 meter length. That's why it is said to be meter bridge. Okay, and from the middle here we will connect to some galvanometer. The galvanometer is connected to, here there is no connection. We connect the galvanometer to some jockey. This is the jockey. This is the diagram of the meter bridge. Then how it will works, let us discuss. This is equivalent to, exactly equivalent to the meter bridge. It is equivalent to the Wheatstone bridge. How it is equivalent to Wheatstone bridge I will explain. Okay, now this is L centimeter means this side 100 and minus L it will be there. Okay, and from A to J resistance we can consider as the P, and J to B resistance we can consider as the Q. Okay, you see here this is equivalent to the diagram, and here we will connect to some battery at here. Then here we have to connect to some battery, like this we have to connect to some battery. This is the positive terminal and negative terminal, and this is the plug key. Now you have to see here, this is exactly equivalent to the Wheatstone bridge. This is exactly equivalent to Wheatstone bridge. How it is equivalent to Wheatstone bridge? I will tell. This is X resistance. Decided with the X, and next X is connected to resistance box, that is R, known resistance, that one. This side is unknown. This is unknown, and this is right side known. Okay, and that is R, and this X is connected to AJ wire. AJ wire is a manganese wire, resistance wire. That AJ wire resistance we are taking as the P. Okay, that is P, and AJ connected to JB. JB is resistance we are considering as Q. Okay, right. And from here, from point P, okay, from one side we are connecting to some battery, right, through the plug key, exactly equal to the Wheatstone bridge. From the middle of the X and R, from the middle of the X and R, we are connecting to galvanometer. galvanometer. This galvanometer is connected to jockey, right? This is the middle of the P and Q. Jockey left side is the P and right side is Q. Middle of the P and Q we are connecting, right? Understood? This is exactly equal to Wheatstone bridge. Exactly equal to Wheatstone bridge. Now let us see how it will works. Okay, how it will works. Now what you have to do? Okay, you have to do the connections like this. Press the jockey at various points on the galvanometer, various points on the meter bridge. First press the jockey at left side. The galvanometer we are using it here. The galvanometer has at the center it has zero deflection. On the left side 30 is there. On the right side also 30 is there. Right, left side and right side 30 is there. Okay, on the that means if the current flows in one direction, it will go deflection right side. If the current direction is changed, the deflection will become left side. If there is no current, the point will be at the middle. Right? That means right side readings are there, left side readings are there. Middle zero will be there. That is the galvanometer, right? Okay, now let us see here. What you have to do it here. You have to press the jockey at various points on the manganese wire. If you will press, what happens? Okay. For example, if you will press the at here, if you press it here, the left side length wire length is L. Left side wire length is L. If you press it here, left side wire length is L. That is a P resistance. If you press it, if you move the jockey right side, left side wire length will be increases. Jockey left side, that is a P. When the wire length increases, the resistance of in the left side also increases. That means P changes. When P changes, automatically Q also changes, because when you press the jockey at here, left side wire length is increased, right side wire length is decreased. That means Q decreases. Like this, by changing the values of P and Q, you adjust the galvanometer deflection as 0. When current of the galvanometer is 0, then at the moment we know the Wheatstone, it follows the Wheatstone bridge principle. That means now what we have to do, by pressing jockey at various points, at various points at various points on manganese wire, meter bridge wire. At a point, galvanometer, by pressing jockey at various points, press the jockey at various points on manganese wire until galvanometer shows zero deflection. Okay, at a particular point, the galvanometer shows the zero deflection. Okay, that point is called as the balancing point. That point is called as the balancing point. Okay, that is for example, this is the point at which the galvanometer shows the zero deflection. This point is said to be balancing point. Then note the balancing length. Note the balancing length as L. Okay, from the left end you have to take the balancing length. At this point, if the galvanometer shows the zero deflection, this point is said to be balancing point. That point distance from left end you have to take that as L, balancing length. Then the potential difference, we know that when the current through the galvanometer is 0, then we write one thing, what? X P by Q equal to R by S, we write P by Q equal to R by S. This resistance X by R equal to P by Q, we write X by R. This resistance by this resistance equal to this resistance by this resistance. X by R equal to P by Q, we write. But P proportional to length, P proportional to L, and Q proportional to its length. Jockey left side wire length is L, its resistance is P. Resistance proportional to length. That's why here instead of P by Q, we write their lengths also. X by R, that P length is L and Q length is 100 minus L. Then we write like this. And finally, we will get the formula for the X. X is equal to, we will get as R into L by 100 minus L. This is the formula to find out the unknown resistance. What is that? L by 100, X is equal to R into L by 100 minus L. This formula we will use to find out the unknown resistance. In this formula, what is R and what is L? Okay, you take the screenshot. I'm going to move in upward direction. So what is R in this? What is R? Right? Is it clear? If you have any doubt, you write in the chat box. R is the resistance in the right box. Resistance in right gap. Resistance in right gap. Okay, resistance in the right gap. This is the known resistance. Is it right? This is the known resistance. Okay, what is L? What is L? L is the balancing length. Balancing length. Balancing length means at a particular point, the jockey is pressed at various points on the galvanometer. Right? Is it right? You see here. This is said to be jockey. J is said to be jockey. Okay, follow the cursor. Jockey pressed at various points like this. At a particular point, the galvanometer shows a zero deflection. That point is said to be balancing point. That point distance from left end is said to be balancing length. That we can note as L, right? And the balancing length. Balancing length from where to where? That is AJ. AJ is equal to left end to J. That is the balancing length. Okay, that is L. Then, if you know that one, then directly we can find out the X value. X is what? Unknown resistance. That means that wire resistance we don't know. That unknown resistance are the resistance in the left gap. Resistance in left gap. Resistance in left gap. Understood, students? This is the method that how to find out the unknown resistance by using meter bridge. Here we got how to find out the unknown resistance. Next, I am going to find out the specific resistance. How to find out the specific resistance by using meter bridge. Specific resistance of a wire. How to find out the specific resistance of a material? There is a formula for the specific resistance. Rho is equal to, previously we know that the specific resistance formula is rho is equal to RA by L, where R is the X, R is the unknown resistance here. Unknown resistance is X. Unknown resistance, specific resistance of unknown material I am going to find out na. That unknown material resistance is X, and area of cross section we will take as a pi r square. But R radius we can find out by using the screw gauge. L is the length of the wire. If you substitute the length of the wire and radius and unknown resistance here we are measuring, and radius we can measure with the screw gauge, and length directly we can measure by using the meter scale. Okay, this is the length of the wire. R is the radius of wire, and X is its resistance. X is the resistance. If you substitute all values, you will get the specific resistance. Okay, right? This is the how to measure the unknown resistance and specific resistance by using meter bridge. Next, I am going to start the potentiometer. Right? What is potentiometer? How we can find out the what is the use of the potentiometer? This is very important. You listen very carefully. Okay. If you have any query, write in the chat box. If you have any query, write in the chat box. Okay. Very important topics I am going to explain fastly. Right. Next topic. Next topic is the potentiometer. Potentiometer. What is the use of the potentiometer, and what is the construction of the potentiometer, and how it will work? Okay, first, potentiometer construction will be like this. There, it has 10 separate 1 meter wires. This is a point. Okay, like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are so many wires are there. Okay, right? And now I will draw only some. That's enough. No need to go for all. Right? Potentiometer has 10 separate 1 meter wires. Okay, this is B point. This is 1, 2, 3, like this. 10 separate manganese wires are there. This is a manganese wire. Manganese wire, resistance wire. The manganese is an alloy, it's a resistance. They are connected with copper strips. This is a copper strip. Copper strip. Copper strip is a conductor. We will connect like this. like this we will connect. That means we are making guys one wire. These are fixed. This is fixed on a wooden scale, wooden board. Okay, this is a copper strip, and next this is a copper strip like this. This is the end point. This is the P point. This is the potentiometer. It is a on a wooden board. 10 separate 1 meter wires connected parallel to each other connected by using copper strips, not parallel. Okay, they made only one wire like this, right? And now these are connected to some battery like this. This is a battery. This is the primary circuit. This battery EMF is E0, and this we are connecting to some plug key. The plug key is K, and we are connecting to some rheostat also. This is the rheostat, whose rheostat resistance is RS, series resistance. Like this we can connect. Okay, right. This is connections, and now current will flows in the circuit. The current starts from the positive terminal of the battery. Okay, the current flows like this. Current flows like this, like this. Current starts from the positive terminal and go. It will travel like this, like this, like this, like this. Then it will go like this, right? Then we want the current formula in this. Okay, for example, I want the this is a wire. This wire length is small l. Okay, wire length is small l. I want the potential difference across this wire. This is the potential difference. Okay, right. Now what happens? Potentiometer has a potentiometer has potentiometer has 10-meter wire. Okay, right? Potentiometer wire. Now the potentiometer wire resistance capital R we can consider as the resistance of potentiometer wire. Resistance of potentiometer wire. Capital R is the resistance of potentiometer wire, and RS is the series resistance. That is the resistance of the rheostat in the figure, and E0 is the EMF of cell. Okay, K is the plug key, and now I is the current in the circuit. For example, I is the current in the circuit. Current in circuit. Okay, now how to find out the current in this circuit? Current formula, current in circuit we can write like this. Current is equal to effective EMF by effect resistance. Effective EMF is E0, and effect resistance, total resistance in the circuit is the internal resistance of this cell we can consider as the R0. Okay, R0 is the internal resistance of cell. Then we write as total resistance. So rheostat resistance is RS, internal resistance is R0. This AB wire resistance is potentiometer wire is AB. Okay, its length is 10 meters. Capital L is the length of potentiometer wire, that is 10 meters, right? Then we write here total resistance as R plus RS plus R naught. It is the formula for the current in the potentiometer. Current in the potentiometer. Next, I want the capital L is the length of potentiometer wire. Capital L is the length of potentiometer wire. What is the length? Length of potentiometer wire. Potentiometer wire length, how much it will be there? The potentiometer wire length is 10 meters. Okay, and the capital is the resistance of potentiometer wire, that is A to B length. Okay, understood students? I want the potential drop, potential difference, potential difference across smaller length of potentiometer. What is the potential difference across the smaller length of potentiometer? Then that smaller length resistance we can consider as R dash. Then V is equal to IR dash according to Ohm's law. R dash we write as R dash is the resistance of this one. We write as rho L by A, rho L by A. Okay. Here we write V is equal to I into R dash value we write as rho L by A, rho L by A. From this we write as V is equal to I rho by A. This I rho by A we can consider as the phi L. Okay. This from this we write as V proportional to L. This is called as the potential difference is directly proportional to length of wire. This is called as potentiometer principle. What is the principle of potentiometer? You take the screenshot right here. Okay, this is the principle of potentiometer. This is the principle of potentiometer. This is the principle of potentiometer. Principle of potentiometer. Okay, right. What is the principle of potentiometer? The potential difference across the potentiometer wire. Potential difference across the potentiometer wire directly proportional to its length. Okay, right. In this case, here we are having the phi. This phi is called as the potential gradient. Okay, the principle of potentiometer is principle of potentiometer. Very important. Okay, principle of potentiometer is that V proportional to L is the potential difference across the potentiometer wire directly proportional to its length. Okay, this is the principle of potentiometer, and from this we got as the phi, where phi is the V is equal to phi L, V is equal to phi L. Okay, if you will remove the proportionality, V is equal to phi L we are getting, where phi is called as the potential gradient. Phi is called as the potential gradient. What is potential gradient? Potential gradient formula is what? Potential gradient means potential drop by length. Right from here, phi is equal to V by L. V by L is the potential, V is the potential drop by length. Potential drop by length, phi equal formula. Potential drop, potential gradient, potential drop per unit length. This phi formula we write as I rho by A. Okay, this is some basic information regarding the potentiometer. Now, very important two questions I will explain. More 15 minutes takes to complete this chapter. Okay, one is how to compare the EMFs of two cells by using this potentiometer, and how to determine the internal resistance of a cell by using this potentiometer. If we complete these two, then this chapter will be complete and more 15 minutes takes place, and you listen very carefully. Okay, that this is the basic information regarding the potentiometer. The potentiometer use is there now. I'm going to erase this. Right, first, very important, I think till now in the last 20 years 10 times it will come, I think. Mostly either problem or concept it comes in the board exam. Okay, and you prepare properly. First, comparison of EMFs of two cells by using comparison of EMFs of two cells. Comparison of EMFs of two cells. If you want the clear explanation, go for the previous lectures. In the previous lectures, one topic 1 hour is there. Okay, comparison of EMFs of two cells by using potentiometer. In this, in 1 hour, all the topics we are covering, right? That's where somewhat speed it will be there. Comparison of EMFs of two cells by using potentiometer. How we can compare the EMFs of two cells by using potentiometer, that I am going to explain. You listen very carefully. It was very simple. Okay, all right. We can go for the first potentiometer, right? This is the A wire. Potentiometer has, you know that potentiometer has 10 separate 1 meter wires. Okay, this is the first wire, the second wire, third wire. Experiment also we did, na? Uh, right? Based on this, how to compare the EMFs of two cells, like this. This is the potentiometer wire. This is A point, and here we have to connect to some battery. Right? This is the battery. This is a plug key, or otherwise here we can connect some rheostat. This rheostat resistance is Rs, and here we can connect to some plug key. This is connected to point B, right? And here this is the positive terminal and this is the negative terminal, and from here from A point, okay, from A point you have to connect to two cells. Those EMFs we want to compare. This is the first cell whose EMF is E1, internal resistance is R1, and this is the second cell whose EMF is E2 and internal resistance is R2. These two are connected, and this is the 1 point, this is 2 point, and this is 3 point at here. Okay, and here this is a box where we can connect the 1 2 3. This third point we can connect to the galvanometer. This galvanometer is connected to jockey, right, like this. Okay, you see here what is the procedure and what we have to do it here. First, to close the plug key, close plug key K. Okay, what we have to do it here, close plug key K and connect 1 with 3. 1 and 3 if you will connect, first cell is in active, right? First cell is in active. The what you have to press the jockey at various points on the galvanometer, on the potentiometer wire, until the galvanometer shows the zero deflection. What we have to do it here, we have to do one thing, that is first, okay, we have to do the connections like this. After this, what you have to do, this is already potentiometer up to here. Extra we are connecting the two cells whose EMFs are compared on the secondary circuit. Then what we have to do, first we have to connect the 1 3, like this you have to connect. When you connect the 1 3, this cell, second cell is not active, E1 cell is inactive. Then press the jockey to various points on the galvanometer until the galvanometer shows the deflection. Why this galvanometer shows the deflection 0, null deflection? Because until galvanometer deflection 0, you have to press the jockey at various points on the potentiometer wire, like this you have to press this jockey. Then here, why we have to press it? Why it is showing the zero deflection at this point? For example, it is showing the zero deflection at this point. Some potential difference is there across the potentiometer wire due to this primary cell, right? If that potential difference and some terminal voltage is there across the first cell, because first cell is in active 1 and 3, then these voltages are balanced. At that moment, net voltage become 0 and effective EMF become 0, the current become 0 at here, right? That means in this case, according to the potentiometer principle, we write as potential difference across the AJ, we can take as node balancing length as, close the plug key and connect 1 and 3. Okay, press the jockey to various points and note the balancing length as, note balancing length L1. Okay, right, this we can take as AJ1. AJ1 we can take. Okay, that is equal to AJ1. Now what do we have to do it here? Then according to the potentiometer principle, we know that potential difference across the AJ1 is equal to phi L1. This is the potentiometer principle. A2 J1 length is phi L1. Okay, that is the balancing length. Phi is the potential gradient, we know that one. But this potential difference across the AJ is equal to potential difference across the cell. But what is the potential difference across the cell? Potential difference across the cell is nothing but terminal voltage. Okay, potential difference across the cell is the terminal voltage, E1 minus IR we write. But the current through the galvanometer is 0 means actually this is a single path, right? When current through the galvanometer is 0, automatically current through the cell is also 0. When current through the cell is 0, in the open circuit, the potential difference equal to EMF of cell. Is it right? I0 means, okay, then we write as E1 is equal to phi L1. This is equation 1. And now what you have to do, right? Open the 1 3 connection. Open the 1 3 connection, right? Now close. Second case, what we have to do, close the plug key. Now connect the, remove the connection between the 1 and 3, and now connect the 2 and 3. Now connect the 2 and 3. Okay, now connect 2 and 3. Follow the same procedure and note the balancing length as L2. Note the balancing length. Note the balancing length as L2. This is, for example, from here it is somewhere it is coming. That is, we can take as the J2. This is J2. A2 J2 is the balancing length. That is L2 is the equal to AJ2, AJ2, right? Okay. Now again, potential difference across AJ2 is balanced here. Now when the 2 and 3 are connected, second cell is inactive, and second cell is inactive, again the current through galvanometer is 0, means potential difference across the AJ2 equal to potential difference across the cell. Okay, they will be balanced. Net potential difference becomes 0, net EMF 0. That's where current does not flows, right? What is the why the here due to cell, this cell, some potential difference is there across the cell, and due to this battery some potential difference is there across this wire. That potential difference are equal, means then net EMF 0, current will become 0, right? At the moment, then according to the potentiometer principle, we write V2 equal 5L2, but again V2 we write as V2 we know as potential difference across the AJ2, but that is equal to potential difference across the second cell, because second cell is inactive when 2, 3 are connected. Potential difference across the second cell we write as E2 minus IR2, because V equal to E minus IR formula we know, but current through galvanometer 0 means current through the cell also 0. Here 0 means this is the path, this is the path. When here 0 means galvanometer showing 0 current means current through the cell also 0. Then current through cell 0 means E2 minus 0 R2 we write. Then we write as V2 is equal to E2. Then we will get E2 is equal to 5L2. V2 we will get as 5L2. This is equation 2. Then we have to find out the ratio. That is E1 by E2 is equal to, you divide the equation 1 and 2, then what you will get? If you divide the equation 1 and 2, 1 minute. Right, students? Now you divide the equation 1 and 2. Equation 1 by equation 2 you can do. Equation 1 by equation 2. If we do, then what you will get? E1 by E2 is equal to 5L1 by 5L2. 5 cancel. Then we will get as E1 by E2 is equal to L1 by L2. E1 by E2 is equal to L1 by L2. Little problem it is facing. Oh, wait for 1 minute. Five L2 we will get, this will cancel. Then E1 by E2 we will get as E1 by E2 we will get as L1 by L2. This is how to compare the EMFs of two cells by using potentiometer. Just for the first cell you have to note the balancing length, and for the second cell also you have to note the balancing length. For the first cell 1 3, if you will connect, the first cell is inactive. First cell is inactive, and press the jockey to various points and note the galvanometer deflection as 0. When the galvanometer deflection is 0, then at that point at J1, if it is the galvanometer deflection shows the 0, press the 1 and connect 1 and 3. Press the this jockey at various points. at a particular J1, at a particular point J1, if the galvanometer shows the zero deflection, that point distance from left end is a balancing length, that is L1. Note it, E1 equal to 5L1. Second time, what you have to do? Remove the connection between the 1 and 3, connect the 2 and 3. Second cell is inactive. Follow the same procedure. Note the balancing length is L2. Then E2 equal to 5L2. Divide them, both of them. At E1 by E2 equal to L1 by L2. When you substitute the L1, L2 values, automatically you will get the E1 by E2. This is how to compare the EMFs of two cells. Okay, completed. Students, more 10 minutes. Right, the next one is second important, most important application, that is how to determine the internal resistance of a cell. Determination of determination of determination of internal resistance of a cell. Right, I think now it is clear. Now I am going to start. It is working from last 1 hour. That's why I think it is unable to work continuously. Okay, even though we want to complete our work, uh, this is the potentiometer again. Okay, only 5 minutes. Only 5 minutes I will take. In 5 minutes, I will complete the most important topic. Very, 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 very important. Okay, this is the potentiometer wire, and this is the primary circuit, and this is the cell whose EMF is inert, and this is some rheostat. That rheostat resistance is RS, This rheostat resistance is RS, series resistance. We are connecting to some plug key, right? That is K, and then we are connecting to AB. And then this is the primary circuit. Already we know that one. This circuit is already previously we discussed from the basic. Next, I want the cell whose internal resistance is to be determined, that is connected at here at point A. This is the cell whose EMF I want to determine. This cell EMF is E. Its internal resistance I want to determine. Its internal resistance is smaller. That smaller I want to find out. And we are connecting some parallel resistance at here, and along with some plug key, that is K1. And the next we can connect these two like this, and then this is connected to some galvanometer, and this galvanometer is connected to some jockey, right? That's all. This is the circuit diagram. Then let us start how to do the connections. All the positive terminals should be connected together. Remember, this is the positive terminal, this is the positive terminal, this is the positive terminal. Positive terminal connected to point A. Okay, right? Let us start how to find out the interrelations of a cell. First, what you have to do, close plug key K, close plug key K. Now clear now, students? Is it clear now? Is it appearing? Right. Close the plug key K and open K1. So when we open this K1, this resistance, parallel resistance will not work. This will not work. Remember, this is not there. This part is not there. Why? Because this K1 is open means current does not flow through this. Current does not flow through this. Then current, what you have to do? Press the jockey at various points. Press jockey at various points. Note the balancing length. Right? How to note the balancing length? You know already. Press the jockey at various points on the potentiometer wire at a particular point. At a particular point, galvanometer shows the zero deflection. Note that point distance from the left end. This point is said to be balancing point. That balancing length you have to note. What you have to do it here? Note balancing length. Note balancing length as L1. Note balancing length as L1. Now what you have to do? How we are noting the balancing length? Just first K1 is open. This will not work. Only cell is in working. Press the jockey at various points until the galvanometer deflection. Galvanometer shows the deflection 0. Okay, null deflection. Then at this location, if the galvanometer shows the 0 deflection, this point distance from left end you have to notice the balancing length, that is AJ. This AJ1 is the, you can take as L1. Okay, this location we will take as the J1. And the next, according to the potentiometer principle, what you know? Potentiometer principle. Do you know what is the potentiometer principle? V is equal to phi L, right? Potentiometer across the AJ, V1 is equal to, we write as phi L1. Okay, but we know V1 is the potential difference across the AJ. This potential difference across the AJ, but galvanometer showing that zero deflection means the potential difference across the AJ must be equal to potential difference across the cell, because cell is in the working now, right? When the current through the galvanometer is 0, the potential difference across AJ equal to potential difference across the cell. What is the potential difference across the cell? E minus IR. E minus IR. But the current through the galvanometer is 0 means current through the cell also 0. That's why we will get as E only. Then we will get as E is equal to phi L1. This is equation 1. And the next, what you have to do? Close plug key. Close plug key K2 also. K1 also you can close. Okay, now you have to close plug key K1. Okay, now you have to close the plug key K1 and K also. Then what you have to do? No, again follow the same procedure. Note balancing length as L2. Okay, follow the same procedure means press the jockey at various points until the galvanometer's deflection becomes 0. Now, for example, at this location, if the galvanometer shows the 0 deflection, This location you take as J2, okay, and note the balancing length from A to J2, right? Note balancing length as L2, as L2. Now again, according to potentiometer principle, again what you have to write, V2 is equal to phi L2 we have to write. But V2 is what? V2 is the potential difference across the AJ2, because at the second point is the second balancing length is J2. Then here also current through the galvanometer is 0, it is showing, right? Then only balancing length you have to note as L2. But here this is AJ2, AJ2 equal to L2. But here the galvanometer deflection, potential difference across the galvanometer shows the 0 deflection. Potential difference across AJ2 equal to potential difference across the cell. But one thing is that here the current through the galvanometer is 0 means when the plucky K1 is closed, the cell also inactive. That's why the current will go in this path, in the closed path, in this path, current will go, but the current will not come outside. Current to galvanometer is 0, it is showing, because we are noting the balancing length at 0 deflection only. That's why there is a chance to flow the current through the cell. That's why V2 never equal to E. That's why we can take as V2 as V is equal to phi L2. This is equation 1. Here V should not equal to E. Remember that. Then we have to simplify this. Then how to simplify this? Okay, within 2 minutes I am going to complete. Right. Next, to divide the two equations. What you have to do? Equation 1 by equation 2 you can do. When you will do these two equations, E by V is equal, we will get as phi L1 by phi L2. Phi cancel, L1 by L2 we will get. But EMF formula there is there. EMF formula. We know EMF formula in this current circuit formula is what? In this current, in this closed path, if the current, if you want, right, effective EMF is E. In this current formula is capital R by plus small r we write. From this EMF is equal, we write as I of capital R plus small r we write. Current formula in this circuit, current outside is 0. Current in this circuit, because K1 is closed in the second time. K1 is closed means current in this flows, right? Outside it will not flows. That's why the current we write as effective EMF, total EMF E, total resistance is capital R plus small r. Then from that we write as E is I of capital R plus small r. V is the potential difference. Potential difference what we write? Potential difference formula, potential difference across the cell. We can also write as V is equal to IR also. This we substitute here. Then I gets cancelled. Then capital R by small r, capital R is 1 plus small r by R is equal to L1 by L2. If you simplify this, then we will get the small r formula directly I am giving. That is small r is equal to L1 by L2 minus 1 into capital R. This is how to determine the internal resistance of a cell. L1 is the balancing length with only cell. L2 is the balancing length when the first one is what? L1 is the balancing length. Open K1 means resistance is not in work, right? Only when cell works in the secondary circuit, the balancing length is L1. Across the cell, if you connect some capital resistance parallel, K1 is closed means capital resistance we are connecting parallel. At the moment, balancing length is L2. Then, if you substitute capital R is the parallel resistance. If you substitute them, then you will get the internal resistance of a cell. This is the how to determine the internal resistance of a cell, where R is the internal resistance. With this, our chapter is completed. Thank you to all. Thank you to all.